Welcome everyone. In this video lecture, we will solve a diode based numerical from the Microelectronics circuits book. So in this question, it is given when a 50 ampere current is applied to a particular diode. So a diode is there. I am making the diode. Okay. Example, this one is diode. Okay. So a 15 ampere current. Okay, this one is ampere. 15 ampere current is flowing to that particular diode. Okay, this one is diode. Clear? It is found that the junction voltage immediately becomes 700 millivolt. So at that time, the junction voltage is say 700 millivolt. Okay, when this 15 ampere current is applied to this particular diode. Okay, after certain time, immediately becomes 700. However, as the power being dissipated, after power being dissipated, the diode voltage becomes 580 millivolt. However, as the power being dissipated in the diode raises its temperature and the junction voltage becomes 580 millivolt. So what we can write here means after power being dissipated, dissipated, the value of VT2, or we can write it VD2, the voltage across the diode becomes 580 millivolt. So I am writing VD1, VD2. Okay. Means initially when we are applying 15 ampere current, so the voltage across the diode is 700 millivolt. After power being dissipated across the diode, it raises the temperature across the diode, which causes decrease in the voltage, that is about 580 millivolt. Okay, that 580 millivolt occurs with increase in temperature. Okay, with increase in temperature. Okay, so now, so the voltage drop across the diode, so the resultant, or we can say the voltage or resultant voltage drop across the diode can be written as Vd equals to how much? Initially this one is Vd1, now it is Vd2. Okay, so how much it is? 120 millivolt. Okay, so how much voltage drop? So the resultant voltage drop across the diode is 120 millivolt. Okay, initially 700. So resultant voltage drop we can say Vd1 minus Vd2. 120 millivolt is the resultant voltage drop across the diode. So what it gives? So as we know, so this one is the 580 millivolt. So we have to find the what is the apparent rise in junction temperature. Okay, what is the power dissipated in the diode in the final state, and what is the temperature rise per watt of the power dissipation. That is our thermal resistance. Temperature rise divided by power dissipation in watt. Okay, so this one is the resultant voltage, we can say 120 millivolt. So we have to find the first temperature. What is the apparent rise in temperature? So as we know, one very fundamental thing, as we know, for every 1 degree centigrade rise in temperature, the diode voltage decreases by 2 millivolt. Okay, means one can also write like this: as temperature increases, okay, as temperature increases, Vd decreases by 2 millivolt per degree centigrade, 2 millivolt per degree centigrade. Okay, so means what we can say, means for 2 millivolt change, the temperature is 1 degree centigrade. Okay, so there is the change, resultant voltage drop change, we can say voltage drop change across the better trend voltage VD 120 millivolt. So for 120 millivolt, the resultant temperature change can be written as 2 millivolt by one simple unitary method. So this should be cancelled out. So 2 into, so it should be 60 degree centigrade. For 60 degree centigrade, the resultant change will be what? 120 millivolt. Okay, so we can say the, hence the rise in junction temperature will be will be 60 degrees centigrade. Okay, this one is the first one, because initially in the question what is given, when 50 ampere is current is flowing through a particular diode, VD voltage is 700 millivolt, but after some time the power being dissipated and temperature increases and the voltage become how much, 580 millivolts. So resultant change in the voltage drop will be VD1 minus VD 120 millivolt. So 120 millivolts. So how much temperature increased? So as we know, for 1 degree centigrade rise in temperature, there is a 2 millivolt decrease in the diode voltage. As temperature increases, VD decreases by 2 millivolt per degree centigrade. So in 2 millivolt, 1 degree centigrade change. So for 120 millivolt, how much change in temperature? 60 degree centigrade. So this one is the rise in the junction temperature is 60 degree centigrade. So this one is our first part. Okay. Second, what is the power dissipated in the diode in the final state? What is the power dissipated? We have to find the power dissipated. Okay, in the diode at final state. Okay, what they are asking, what is the, see here it is. Okay, right. What is the power dissipated in the diode in the final state? So power, okay, so P equals to VI. So right, power equals to VI. Okay, so what should be the V in the finally 580 millivolt will be the V, because after power dissipated the voltage across the diode will be VD, that final voltage VD will be, VD final will be simply 580 millivolt into I, means how much current is flowing, already given 15 ampere. So 15 ampere. So 580 into 15 into milli 10 to the power minus 3, or we can write it 580 into 15 into 10 to the power minus 3. So if we solve, this power will be 8.7 watt. This one is the second part. Okay, first part we have calculated rising temperature. Second one, power dissipated in the diode at the final state. Final state, the voltage across the diode is final 580, current 50 ampere. So multiply this one into 10 to the power minus 3. Okay, now what is the temperature rise per watt of power dissipation? Number C. In C, they are asking temperature rise, okay, divided by power dissipation. Power dissipation in watt. This one is called our thermal resistance. The whole thing is called a thermal resistance. Okay, once again I am showing you the question. It is also given thermal resistance. What is the temperature rise per watt of power dissipation? Temperature rise per watt of power dissipation. Means temperature rise divided by power dissipation. So temperature rise is how much? 60 degree. 60 degree. So once again I am writing here that okay. So the thermal resistance nothing but simply the temperature rise. So temperature rise will be 60 degrees centigrade. So write it 60. Then power dissipation is simply 8.7 watt. Okay, so if we solve this one is 6.9 degrees centigrade per watt. Okay, so this one is the other answer. So this is our third part. Okay, this one is our third part. So this is our answer. Clear? So once again, this one is what? Thermal resistance. Temperature rise divided by power dissipation. So we have rise temperature 60 degree and this one the power dissipation at the final state. So 6.9. Okay. Power dissipated at the diode at the final state power VDI. VD final VD value is 580. So after calculation it is simply of 8.7. Rise in temperature. Rise in temperature we have calculated like 60 degree for 120 millivolt 60 degree. Okay. And the resultant voltage drop change across the diode will be this. So 120 millivolt. So for 2 millivolt 1 degree centigrade rise in temperature. For 120 it should be simply 1 degree centigrade by 2 millivolt into 160 degrees. Okay. So 60 degrees centigrade is the answer. So this is all about this question. This is a very interesting question and this is for the microelectronics circuit book. So this is all about this question. So thank you for watching this video. Thank you.